Hello everyone, I'm Xiangyu Pen. I'm going to present our work crafting better contrastive views for Siamese representation learning. This is a joint work with Kai Wang, Zhen Zhu, Ma Wang, and Yang You. Contrastive learning has achieved great success in computer vision. The core idea of contrastive learning is to pull positive pairs closer while pushing apart negative samples in the embedding space. A series of contrastive learning methods have been proposed in recent years, including SimClear, MoCo, UROL, and SimSiam. A common ground shared by these methods is the Siamese structure, which aims at optimizing the distance between positive samples. An important issue in contrastive learning is the selection of positive views. Most existing works use a conventional random crop as an approach to generating positive views. However, we find the random crop may not be the optimal cropping strategy for contrastive learning. The first problem is false positive. An example here is object versus background, even if the two views are from the same image. Another problem is trivial pair, which means that the positive views are too similar for optimization. In this work, we propose contrastive crop, which is tailored to make better contrastive views. Unlike random crop, contrastive crop takes semantic information into account so that the crops won't miss the object in most cases. It also increases variance between positive views, so that more meaningful representations could be learned through distance optimization. Specifically, we propose the Semantic-aware localization module. It generates a bounding box of the object from the heat map. We then use the bounding box as a guidance to generate crops. Note that we only restrict crop centers in the box so that some related background texture could also be included. Then we apply the center-suppressed sampling. It adopts a center-suppressed distribution over the area of the bounding box. Compared with uniform distribution, it has lower probability near the center and higher probability at other positions. By increasing the sampling variance, we could obtain crops of smaller overlap and less similarity. Here, we compare the sampling effect of the two cropping strategies qualitatively. Applying random crop twice results in some false positive pairs, which are marked in yellow. Our contrastive crop largely avoids such bad cases while maintaining a large variance between positive views. We also make a quantitative analysis. We evaluate the sampled positive pairs by a standard ResNet 50 trained with ImageNet labels. We use the confidence score of the ground truth class as an indicator of semantic information in that crop. And positive similarity is calculated in the embedding space. We can see that views from contrastive crop convey more semantic information than random crop at the same level of similarity. Moreover, with equal semantic information, contrastive crop achieves smaller similarity or larger variance than random crop. We conduct extensive experiments to validate the effectiveness of contrastive crop. We first show the linear evaluation results. Contrastive crop achieves 0.4 to 2% accuracy improvement on small datasets with different contrastive learning models. It also brings accuracy gain on ImageNet 200 and the standard ImageNet 1K. This shows that contrastive crop could apply to different datasets and different models well. When transferring to downstream tasks like object detection and instance segmentation, models pre-trained with contrastive crop consistently outperform those original ones with random crop. These experiments show that views selected by contrastive crop could help models learn better representations in contrastive learning. Thank you very much for your attention. Please make sure to check out the webpage or scan the QR code for code and updates on contrastive crop.